So today is part 2 of monads and all that. I'm going to talk about monad transformers. So let me first of all remind you of a little bit of what we saw yesterday. So we looked at two monads in quite a lot of detail. First of all, the state monad, represented by functions from states to values in new states. We looked at the maybe monad to represent computations that may fail. And if you had time to look at the exercises that I put up, then you will also have looked at the list monad. So what you see here, this is not real Haskell, it's pseudo-Haskell. But it's the way that the list type would be defined if you could write this. So it says that the type of lists of A's, that open close square bracket is not the empty list, it's the name of the type. List of A's is either an empty list, just like nothing, or it's a cons. This is the Haskell cons operator applied to an element and another list. So if you compare the type definitions for the maybe type and the list type, you can see that they're very similar. They're both types with one parameter. They both have a case, a kind of empty case, nothing on the empty list. The only difference is that when maybe represents success by just A, then the list type gives us both an A and another list, more A's. So lists behave, if we think of them as a monad, very much like the maybe type plus backtracking. Because when a list computation succeeds and it gives you a value, you still have another list of more values that you can try later if you don't like the first one. Oh, I discovered yesterday that not everybody knows what backtracking is. Backtracking is an algorithmic technique that you can use in search algorithms where you try one alternative and if that doesn't work out, then you backtrack, you return to a previous state, and then you try a different alternative instead. And the list type in Haskell gives us a monad that is suitable for backtracking. It's particularly important that Haskell uses lazy evaluation here, because that means that when a list computation succeeds, and when we get one value, these other values are not computed yet. And that's like a backtracking algorithm. You get one result, and you have something that will enable you to compute other results on demand. But of course, they haven't been computed yet. Okay, so there's three monads that we saw yesterday. So I've just talked about how similar maybe and lists are. Both of them give us a way to represent failure, nothing or the empty list. Both of them offer a way for us to combine alternatives, to combine different possibilities. Think of that as like the catch function that I mentioned yesterday for maybe, a function that provides a handler for failure. So since they behave in a similar way, wouldn't it make sense to define a common interface that represents those things? And we can do that via another Haskell class. So this is another of the classes in the Haskell standard prelude. You can read this definition as, if a type M is already a monad, then it is also a monad plus if it has implementations of these two operators. And M0 is going to be what we call the operator that represents failure, while M plus is a function that can combine two computations into, oh, there should be a space in there, into a third one. So this combines alternatives. Okay, so if this is to be an interface to both lists and maybe type, then we should see how to implement it for both types. And here are the implementations. So maybe is a monad plus, where M0 is nothing. And what M plus does is just look at the first alternative, and if it failed, it picks the second. But if the first alternative succeeded, then we're done. M plus will also succeed with the same result. If you look at the list instance on the other hand, then M0 is the empty list, of course. M plus looks at the first argument, and if it's failed, it just takes the second in exactly the same way. The difference is that if the first alternative succeeds, then we don't throw away the second one, because it still provides alternative values for the computation. And if the first argument succeeds, then it will also provide some backtracking possibilities, which we don't want to throw away either. So the right way to define M plus for lists is to say, if the second argument is A cons A's, then we'll succeed, we'll make a cons with A as the first result, but combine the remaining elements using M plus so that we can still backtrack to all of the alternatives that we had before. Okay. Do we recognize this definition? Okay, I've just talked about keeping the alternatives. If you look at M plus, it's just the append operation on lists. So in fact, I wouldn't need to write this out explicitly, of course. I just say M plus equals append. So it's kind of nice that the append operation reappears as a natural part of this monad plus implementation. Okay, so I claim that lists are good for backtracking. Let's take a typical backtracking algorithm and see what it looks like expressed using the list monad. So here is a solution to the n queens problem. Everybody's familiar with n queens, I'm sure. The problem is to place n queens on a chessboard so that no queen threatens another one. And this solution takes the number of queens we want to place as an argument. It's recursive in that number of queens. And it backtracks to search for a solution. The result will be a list of rows in which those queens are placed. So you have to place one queen per column. All you need to know is which row to place them in. Okay, so here we are. If we have 0 queens to place, well, the empty list is the right result. If we have n queens to place, let's first of all place m minus 1 of them, and then let's pick a position for the next queen. So fold R1 m plus map return 1 dot dot 8 does that. It says that we may consider any of the rows from 1 to 8. This is a very Haskell-ish style. Let me just explain it. 1 dot dot 8 is the list 1, 2, 3, 4, 5, 6, 7, 8. When I map the return operation over that, that'll give me a list of monadic computations, return 1, return 2, return 3, and so on. And fold R1 just combines them all with the m plus operator. So that represents what you see in this blue box here. Return 1, alternatively with m plus, return 2, return 3, and so on. So now this is going to explore all possible ways of placing m minus 1 queens and all possible rows in which we might place the next one. And then finally, let me just say that if my safety predicate, which I won't show you the code of, says it's safe to put q there, then I can return q cons q's as the solution. Otherwise, I have to fail. So I use m0 for that. And if I fail, then that will cause me to backtrack and try different values for q and q's. So what you see here is I'm conditionally failing, and that's quite a useful thing to do very often. And so in fact there's a function in the monad library, guard, that just says, if the Boolean is true, then do nothing or return the empty tuple, otherwise m0, fail. So that I can rewrite the code a little more concisely like this. Okay, so does it work? Well, I can call queens 8 to solve the 8 queens problem. And here I've just specified which type I'm calling it at. Because if you look at that code, it's all written in terms of monad plus operators. So in other words, the type checker can't tell that I really mean a list. So I have to tell it. So let's say I want to use the list monad returning a list of integers. And if I do that, then out come a list of 90, whatever it is, solutions to the 8 queens problem. But I can also say, let me run the same code, but hey, type checker, use the maybe monad instead. what will happen then? No, it fails. Why does it fail? Because the first try for each queen is to put it in the first row. So it's going to say, OK, put the first queen in the first row, second in the first row, blah, blah, blah. 8 queens in the first row. Is it safe? No. We failed. There we are. You really need to backtrack to find any solutions. So you can put the maybe monad there. It's not useful, but I just want to show you that you can. OK, so the list monad is good for backtracking. I'm going to show you a classic example of monadic programming. I'm going to use it to construct a backtracking parser. A very simple one. So parsers need to backtrack, right? We'll use list for that. But they also need to consume input. And consuming input, that is a change of state. So I'm going to represent parsers by using a state that is the remainder of the input that needs to be parsed. So when I start parsing something, I'm going to be taking characters off that. And then after parsing something, I'll need to know how much input remains. So I'm changing a state that consists of a string. So those are both monads. That's good. But I need both of them. So what can I do? Well, I've got two monads, state string and list. Let's try putting them together. There's two ways I might do that. I might nest the list monad inside the state one, or I might nest the state monad inside the list one. Okay, those are the only two possibilities. So let's just see, it's maybe not so clear which one of those is right. Let's see which types those actually represent and see which one we want. So if we look at the first one, that actually means this type in the blue bubble, where I've just written S instead of string, but you can translate that in your heads, I'm sure. Okay, so what is an element of that type? Well, it's essentially a function from a string to a pair of a list of A's and another string. Now, the reason that we're using a list here in parsing is we expect that we might be parsing an ambiguous grammar. So there may be more than one possible parse of the same input. But if I use this type, what does it say? Well, it says that for a given input S, yes, I can return many possible parses, but they must all consume the same portion of the input. Because I only get to return one remainder of the input. That makes no sense. Okay, so that's not the right one. What about the other? What type does that mean, really? What is the representation? Well, it's a list of functions from a string to a pair of a parse result and a string. Well, that's better. I get to return a number of different strings, but wait a minute. I have to construct that list. That is, I have to decide how many possible ambiguous parsers there are before I see the input. That can't work either. So neither of those combinations is right. On the other hand, after this discussion, then it's not too hard to see what I do want. And what I want is this type here. I want my parsers to see the input and then be able to backtrack and return 0 or more parses. And for each one, I want a parse result and the remainder of the input. So that's what I want, but I can't get it using the two types that I've got. So, okay. The problem here is that monads do not compose. So if you're given two different monads, monad 1 and monad 2, you could try to compose them by defining a new type like this. Okay, so compose M1, M2 is represented by M1 of M2 of A, so nest M2 inside M1. So you can define that type all right, but it's not a monad. And I hope that the examples that I've shown you will have suggested to you that you're likely to get a silly result by doing this. But you can also try to write the definition of the bind operator. And you just won't be able to do it you don't have variables with the right types to be able to write that definition. So we're a bit screwed here. What can we do? Well, we know what we want, and if we look at that, we can see that it may not contain the state type, but at least it contains the list type. So that's something. So we can reuse the list monad, but we have to do something different with the state. And I don't want to do something special for a state monad combined with lists, but maybe I can do something generic anyway if I parameterize the state monad on an underlying effect, let's call it. So let me define a variation, which I'll call state t, that also takes another monad as a parameter. So this is going to be list in this case, but it could be other monads as well, where the representation is a function from a state to an m computation of a result and a new state. Okay, so first thing you want to ask is this really going to give me a monad? And to figure that out, I need to see whether I can write definitions of the monad operators. So let's do it. How could I return something in a monad with this type? Well, I can take my initial state, and then I have to do an m computation. I have to make something of type m. Let me just use the return of the underlying monad to do that, and otherwise return a pair of the value a and the same state. What about bind? What does m bind f? Well, I have to construct a function that's given the original state, and then I have to do an m computation. So this do here refers to the underlying monad. But I can run the first computation on the original state. It'll give me a pair of an a and an intermediate state, and then I can pass the a to f and run that on the intermediate state to get the final result. So actually the code here looks very much like the code for my original state monad. It's just that I have to take account of this m monad as well. But that was okay. So what we can see here is that state t of s takes a monad as an argument, and it gives me a monad. So it's a kind of function from monads to monads. We call that a monad transformer. Okay, so monad transformers sound harder than monads, don't they? But they're not. So I want you to feel secure about this. All monad transformers are an easy way to build the monad that you want. So in fact, before monad transformers were invented, it was a whole lot harder to use monads because you couldn't build them up. You had to write each one by hand.
The convention belief is that they are harder, so the burden of the proof is on you.
Okay, well, let's hope the rest of the lecture will convince you. Okay, so what is a monad transformer? It's a monad parameterized on an underlying monad, but it's actually useful to require one more bit of structure, and that is a way of lifting underlying computations into the new monad. So we can write, that shouldn't say instance, that should say class. Okay, so we can define a class of monad transformers, which is a parameterized type T with two parameters now, such that for any monad M, we're going to get another monad, T of M, with a lift operation that takes an M computation and turns it into the richer monad, moves it into the richer monad. Can we do that for this state monad transformer? Yes, sure. If we're given a monad M computation, then we can turn that into a stateful computation just by taking the original state and then simply performing M. But all we have to do is take the result of M and see to it that we pair that up with an unchanged state before we return it.
That T of M of A is a monad?
Well, you don't. So the type checker will not require you to restrict T so that T of M is a monad.
But in the cases where you're going to use it, it will happen to be, and the type checker will notice that.
Yes. Okay. This is all very well. Now I've figured out how I can add a state to my list monad, but I also want to be able to backtrack. The list monad is supposed to give me backtracking, but it's now inside the state T. So can I actually write backtracking code using the combined monad now? Well, to do that, I need to write another instance that says that if the underlying monad has the monad plus operations, then I can also implement them for the combined monad. And actually, that's pretty easy to do. So here are the definitions. M0, I can just define by lifting the underlying M0. How do I combine two alternatives, M and M prime? Well, I can just take my state and then pass it to M and pass it to M prime and combine those using the plus of the underlying monad. So that was quite easy. There's a couple of interesting things that we can notice about this definition, though. One thing is, it's very clear here that both the alternatives, M and M prime, run in the same state. And indeed, there isn't really anything else that I could write at this point. S is the only state I've got. So that's going to be very good for backtracking, but it wouldn't be so good for representing exceptions. Why? Because when I write a backtracking algorithm, if I've got a state that is part of my algorithm, and I backtrack, then I would, of course, like to restore the state as well to the point that it had when I made my choice. So if I explore choices, I want to explore choices in the same state. But you will all have used exception handling in languages that support state. So is it the case that when an exception is raised and you enter the handler, the state goes back to what it was before you began the block that the handler is attached to? If it's what? Really?
I think even for backtracking, those cases would be.
Yeah. Okay. Well, for this application, then it seems clear that it's good to restore the state from the previous version. But usually when an exception is raised, then side effects in that block are not undone before you enter the handler. So this would be a slightly strange way to represent exception handling. Okay. Now I'm supposed to be providing state, and we know that I want operations get and put in that case. Can I implement those in this combined monad? Well, yes, it's easy to do. As we've already seen in other examples, all I have to do is to take essentially the same definitions that I had for the state monad yesterday and just shove in a return. And then I'll get code that will work with this new richer monad. So now I've shown you definitions for put and get, both for the state monad that we had yesterday and for the state T monad that I've just introduced. So if I want to define essentially the same operations on two different types, that suggests I should use a class, doesn't it? So let me introduce a class of monads with state. I'll call it monad state. It is, I guess it's the first two-parameter class that we've seen. But the classes can have any number of parameters. So we'll say that a type M, if M is a monad, then it's also a monad state with a state of type S, if we can implement put and get operations with naturally generalized types. Okay, now there's one more thing in practice that we put in this kind of class definition, and that is a functional dependency. So what this red bit over here says is it tells the type checker that when we define instances of monad state, the monad type will determine the state type. So the type checker will then only allow us to write one instance per monad type, and it will also, when it sees a use of a monad state, and it sees that there is an instance that says that the monad has a particular type, then it will just assume that that then is the type of the state. It's not really necessary to add this functional dependency, but it constrains the types of programs that use this kind of monad a lot. And if you don't do it, then you get a large number of ambiguous overloading messages from the type checker. And it's a huge pain, and you basically, if you don't put this functional dependency here, then you have to help the type checker all over the place by telling it what the types of things are supposed to be. And that is very tedious. The kind of thing that happens is that you have a monad, it has an integer state, you write code that uses it, but the type checker is thinking to itself, maybe there's another instance that gives this monad a Boolean state, or whatever. And so it's unable to resolve the overloading for you. Okay. So, what have we got now? Well, I've shown you a class that defines a set of features that we want. That's the monad state class. I've shown you a type, a monad transformer, that adds those features to any monad. And I've also shown you that we can take instances of other classes, like monad plus, that promote other features from the underlying monad to the transformed monad. So this gives me a package of things for using state. If I can do that for state, can I do it for other monads as well? Can I turn other monads into corresponding monad transformers? Well, we've seen the type monad plus as well, the type of monads that let us express failure and alternatives. And we've seen that the maybe type is one instance of that. Can we define a maybe T transformer that adds this capability to other monads? Well, sure we can. It's quite easy. Here's the maybe transformer. So to add the possibility for failure to a monad M, we just use the type M of maybe A instead. So now the idea is obvious. A failing computation will just return nothing at the end, while a successful one will return just X. And can we lift computations from M to this type? Well, yes, just by lifting the just constructor and applying it to the result. So this is a monad transformer. And of course, we also need to write a monad instance for it. Here it is. So assuming that M is a monad, so is maybe T of M. And how do we return an X? Well, as I said a moment ago, we do it by returning just X. And how do we define bind? Well, as in the case of the maybe monad, but we're basically writing the same thing that we did for the maybe monad, except that we have to do it in an underlying monad M. So we evaluate M, we inspect the result. If it's nothing, we return nothing. There should be a return in there. And if it's a just, then we pass the value A to the rest of the computation F. Okay, and then we also have to ask, can we write a monad plus instance for maybe Tm? So have we succeeded in adding this capability? And we can do that too. So M0 will just return nothing in the underlying monad. M plus tries the first alternative first, inspects the result. If it's nothing, it runs the second. And if it's a just, then it just returns that first value. So this also is quite interesting. It makes it plain now that in this case, M prime will see any effects of M in the underlying monad. How come? Because if you look at this code, what do? We first run m, and then if it fails, we run m prime. And there's no question of undoing any effects in between. So that means that this kind of construction is going to be quite good for exception handling, but less good for backtracking. And then, likewise, we would like to lift other features through the maybe t transformer. So the other feature that we've talked about is state. Can we lift the state operations from the underlying monad to maybe tm? Sure. We can just use the lift operation. And this is often the case, that all we have to do to write these lifting instances is use the lift operation of the monad transformer. So it's easy code to write. Okay, so now I've shown you two monad transformers, and we can go on to define more and more of them. And you've seen what we need to write. For each monad transformer, we need to define the type. We need to write a monad transformer instance. We need to write an instance for the class that defines the features we're trying to add. And we need to lift all of the other features through that transformer. So if we have a library with n monad transformers, we're going to need to write a quadratic number of instance declarations. That sounds as though it could be a problem. But actually, in practice, it's not, because there's a small number of interesting monad transformers. And so if n is small, so is n squared. Okay, so now we've actually got two ways of combining state and maybe. So we could try both of them, and I have a little example here to illustrate that they really do behave differently. Okay, so what does this code do? Well, first of all, it puts a 1 in the state, and then there is a combination of two alternatives, the first one of which puts 2 in the state and then fails, while the second one just gets the state. So if we're in state t maybe, then as we saw, state t provides a state, but both alternatives of a choice run in the same state. So in that case, this code will return 1. If we're in maybe t of state, that doesn't happen, and the code will return 2. Okay, so now the nice thing about monad transformers is that we can compose any number of them. So if we've got an underlying monad m, we can form state t of maybe t of m, or maybe t of state t of m, or even use the state t monad twice and have two different states, and so on and so forth. We can make a lot of useful combinations. And indeed, you might ask now, which monad should we start from? So I've discussed starting from the maybe monad and the state monad, but we can actually add those features. So maybe it would make sense really to start from the identity monad that does nothing, and then just use monad transformers always to construct monads with the states that we want. And indeed, maybe t of identity is pretty much, it behaves exactly like maybe, and state t of identity behaves exactly like the original state monad. What is the identity monad? Well, it's basically identity of A is isomorphic to A. So it doesn't add any features at all. The return operation is the identity function, modulo the isomorphism, and bind is just function application.
State transformer twice or more, and you use get. How do you know in which one are you setting or getting the value?
Because you do not write a lifting instance that lifts state operations from the underlying monad to the outer one. So you only have one put and get, and they operate on the outer state. So the question really is, how do you use the inner state? Well, you have to use lift explicitly. So if you say lift put and lift get, those will operate on the inner state. So maybe it's a slightly weird thing to do, but it's certainly possible. Okay. So the whole point of this was to see if I could make a parsing library. So let's see how we can do that now. Well, I want to add a state, which is going to be the input being parsed, to the list monad. And I can do that now with my transformer just like this. I can define a parser type. It'll be a monad also, using the state transformer on a state that is a list of tokens. And that is the list monad. It's a type. It's not the empty list. OK, so there's just one problem with this definition. And that is, I've just constructed a whole lot of instances so that that type inside the parser constructor is automatically a monad, and a monad state, and a monad plus. It's got all of the structure that I want. But the parser type itself is a new type. It's different from all of the old ones, and it doesn't have any of those instances. So what could I do now? Well, I could now write a monad instance for parser that just strips off the parser constructor and puts it back in the right places. So it would be a very trivial instance to write that would just use the underlying operations on the parser type. And I could do the same for monad state and for monad plus and so on. And a few years ago, that's really what you had to do. But it's very, very tedious. So nowadays there is a language extension called new type deriving, which lets me just say, essentially, I know that the representation type has instances of these classes, monad, monad state with a state of a list of t's, and monad plus. Just give me the same instances for the parser type. After all, those types are isomorphic, and in the running code, the representation is exactly the same. So you can simply reuse the same instances as long as the type checker will let you. And this deriving clause allows one to do that. So it saves a huge amount of boilerplate.